finish off chapter 7, and there's still a lot to do. First thing I'm going to do is do some more improper integrals of type 2. That's one with infinities in it. Just a couple more of those. The second thing we're going to do after that is we're going to look at what's called the comparison test, which is basically a shortcut way that tells you whether or not your particular integral is going to converge or not. It doesn't tell you what it's going to converge to, but it does tell you if it's going to work. And then the third thing we're going to do, the last thing we're going to do today, is improper integrals of type 1, ones essentially with vertical asymptotes. So let's get started with this one. If you look at this question here, we know the first step is pretty straightforward because it's always the same. You replace the infinity, in this case positive infinity, with t, and your job is now to integrate that guy. So what technique will we use to integrate that guy? What method?
U sub.
Correct. And the U sub is a little bit tricky. What is it?
-1/x.
Yeah. Now for differentiation, I'll call that -x to -1. So when we differentiate it with respect to x, we can use the power rule. So multiply by the power makes it positive, reduce, you get that, which in turn is that guy. And when you do your cross multiply, you get that. Yeah, I should call it crossover. Now, let's start switching the variable round to u's and see what we get. E to the u over x squared times x squared du. It's going to be the limit as t tends to infinity of a very nice simple integral, which is what u subs are meant to do. Well, if you want to integrate that fellow, you just get e to the u. We return it back to the x's. And so it's that fella. And now we can evaluate at 1 and at t. At this point here, it's a little bit like a plug and chug kind of situation. It goes to e to the -1 over t, take away e to -1. Me personally, I tend to do a little bit of algebra in these kinds of questions first. And the piece of algebra I'm going to do is change these negative powers into that. And the reason I want to do that is that infinity is difficult enough to deal with on its own when it's just infinite, right? That if you start sticking negatives in front of it, you very often come to the wrong conclusion. So when I look at this guy, I'm saying to myself, okay, time to figure out what this is equal to. I can do brute force on this. It's 1 over e to the power of 1 over infinity. Take away 1 over e. Right? Now, what number? I guess I gave the answer away. What number is 1 over infinity?
0.
Right? And so what you're going to get is 1 over e to the 0, take away 1 over e. What number is e to the power of 0?
1.
So 1 over 1 gets you 1. And we have got a number, which means that this thing converges to 1 take away 1 over e. Cool question. Came out nice. That's if that's good, I can move on then. Okay. So won't do very much with this one, but I will set it up. Well, we know this is going to be the limit as t tends to infinity, the integral from 0 to t, sine squared alpha, the alpha. I mean, these are basically dummy variables. Couldn't I call it sine squared x dx, sine squared any letter of the alphabet except t, d, that same letter? And it, mathematically, it would be equivalent. Okay. Now we're going to figure out what to do with this guy. He is not a u-sub. I mean, if it was sine squared alpha, cosine alpha, yeah, I'd do a u-sub then, but this is not a u-sub.
Trig identity.
It is. What one is he?
It's the, I think it's half cosine or minus half.
It's a half, and it's the minus version.
Okay.
Now, I guess I'll put in one more line. I wasn't intending to originally. If I just pull out the half, because it's really a distraction. That's where we are, right? Right, I'm going to talk through the rest. Won't the integral of that be alpha? Won't the integrate of that be some version of a half cosine to alpha? What you got to then figure out is what happens when t becomes infinite, because you're going to replace the alpha with t's, right? Can you, looking just at that, can you look forward? What's your gut feeling? Is that going to converge or diverge?
Diverge?
That's it. And when it diverges, you're pretty much, that's the end of the question, isn't it? So you type in capitals diverge and you move on. Right, now there is 12 and 13. Question 12 and question 13 have integrals. Let's show you them, and then I'll do an example of one. Have a very specific shape to them that requires a very particular method to solve them. Here's question 12, 1 over x squared plus 2. And question 13, is that quadratic? Do you recognize what method I am going to do to integrate this guy? And the same method is going to be used to integrate 13.
Is it partial fractions?
It is. What about that makes you notice it's partial fractions? Because you're right, it is.
Because the denominator is, well, you can factor out an x and then they'd be split into two fractions.
I would agree that would be the most common feature, yes. As a backup, would you agree there isn't a u-sub in the world that will save you?
Mm-hmm.
And would you agree it's not an integration by parts? I'm not even sure how you start that as an integration by parts. So aren't we doing that if it ain't A, B, or C, then it must be D? right? So if you go through all your, what techniques do we have? Power rule, right? Good memory, U subs, X subs, integration by parts. It's got to be somebody, right? So those two are going to be, and as you already noticed, that one can be factored, but actually so can that one. So I'm going to pick my own guy, because there's so few of these questions, I don't want to use them up totally. So this is the one I'm going to do. But essentially, it'll give you the process, right? How to do similar looking ones. Right, that one is closer looking to 13, but that's fine. Now, I'm not going to do all of it because we have a time constraint, but we'll set it up for you. It's going to be that fella from 1 to t. You factor this guy, you get x plus 1, x plus 2 dx. And you're basically going to factor that guy. So we would start with this fella, and you'd split it up like this. And then wouldn't we do all the usual 5 minutes of work and we'd get our answer? Now, I'm not even attempting to do that only because it takes too much time. But I want you to pretend, and it's totally pretend, that the answer ended up being this guy here. Now, if this ends up being correct, I am the luckiest guy in the world. But can you imagine that'll be a half and this will be 3/4, right? Whatever. So you take this guy and you split into whatever it really becomes. And I'm only pretending that's what it is. Then we should be able to do the next stage. So I'm trying to use this as how to do the process. Well, it's going to be 2 natural logs of x plus 1, take away 2 natural logs of x plus 2, evaluated at x equals 1 and x equals t. Are you comfortable about if it was these fractions, that would be their antiderivatives? Then the next stage would be to plug in t. So what's that? 2 natural log of t plus 1. Take away 2 natural logs of t plus 2. Subtract. If you plug in 1 here, you get 2 log 2. Take away 2 log 3. Okay. So what I would then do is try and put this whole horrible mess together. So it's going to be this log, take away that log, take away that log, add that log. So there's a heck of a lot of stuff going on here. So 2 natural log of this, take away 2 natural log of that, take away this fella, and add this fella. Now what I'm going to do, actually in this question I could pull out a common factor of 2, but we pretend that these two numbers are not the same, because they probably won't be. So if you do it the hard way, won't this be t1 squared, t add 2 squared, take away the natural log of 4 plus the natural log of 8. We're almost there. It's the limit as t tends to infinity. Okay, here goes. This guy, take away that guy, take away that guy, add that guy. Don't you end up with a big, horrible fraction? So you have to remember the laws of logs. This has to be combined into a single log or you won't be able to put the infinity in and get sense. Right, if you take a log and you subtract a log, doesn't that mean first guy divided by second guy? Take away the log of 4 and add the log of 8. Right, if you subtract a log of 4, does it go in the top or the bottom?
Bottom.
And if you add a log at 8, it goes on the top. Do you see I've now got this all together? God, this is a long question. Now what I'm going to do is FOIL that. Well, let's cancel them and get 2. FOIL that out and you get 2t squared 4t plus 2. And FOIL this guy out. You get that. Okay, I know the answer. What's the limit of that thing going to be? Forget about the log.
2.
It's going to be 2. Now, can I do that? Divide top and bottom by t squared, or do L'Hopital a couple of times, but it is 2. There's another way. Can't you cover up everything? Just use the highest powers. You see it's 2. So our final answer is it converges. 2. This bit is 2, but the whole thing's log 2. God, that's going to be a long question.
Professor, I think I got confused when you started squaring everything. I don't know what justified that.
Well, it says t plus 1 squared times 2, so I just filed the whole thing out.
Up
Oh,
one
up
other
here?
line. The line above that one you just, yeah, that one.
Right. There's a law in logs that says the multiple of a log is the same as its power. So it says this, essentially. I was using this property. That 2 times the log of b is the log of b squared.
Okay.
It's called the third law of logs. The other 2 are the log of an a plus the log of a b is the log of ab. That's typically the first law. And then the log of a subtract the log of b. Do you know what that one gets you? Because that's the second and last one.
A over b?
Yeah. So I was just using various combinations of those to take that horrible mess to eventually get this slightly less ugly mess.
Okay, thank you.
I had a question.
Yes.
I'm a little bit confused how in the argument it ended up being 2.
Yeah. Okay.
Yeah.
Okay, let's focus on that. How do you find the limit as t tends to infinity of a quadratic divided by a quadratic? There's 3 different methods I can use, all get me the answer 2. And can you think of any technique that would do that?
Is it the one where you divide each or divide by t squared?
Yeah, that one will do. So if you divide everybody in the top and the bottom by t squared, this guy becomes 2, this becomes 4 over 2, this becomes 2 over t squared, this becomes 1, this becomes 4 over t, and this becomes 4 over t squared, and then you make t go infinite and they go zeros and you're left with 2.
Okay, that makes sense.
Right. You could do L'Hopital top and bottom. You could do a shortcut where if it's polynomials, can't you ignore all the terms except the leading terms? And that gets you 2 as well if you do that method. That was a big, long question, actually longer than I thought it was going to be when I originally started it. That is as far as I want to go with type 2. So let's move on to what's called the comparison test. Now, what the comparison test will do is it will tell you whether or not the integral you're interested in converges or diverges. It will make no attempt to tell you what the number is if it converges. So in this method, you will get numbers, but those numbers are not the answer to the integral you want. Those numbers are just there to convince you that it converges. See, if the answer is infinite, it diverges. If the answer is a number, it will converge. So what does the comparison test do? Well, there are really only a few things we compare it to. So let's look at what those are. The one doesn't matter. It could be 22, who cares? Would you agree? And if you don't, will you just believe me? Oops. That 1 over x squared eventually converges. Can you pretend that I've done that? Because it does. Would you agree that 1 over x, that guy, will you just trust me that it diverges? It's a log and it doesn't work. So we have this property. If you ever get an integral that's 1 over x to the power of something, and we're calling this power p, right? 1 over x to the p. If p is greater than 1, so p is 2 like x squared or 3 like x cubed, then it converges. And if p is less than or equal to 1, then it diverges. So we are going to look at how do you compare polynomials, rational functions, polynomials top and bottom, and decide whether it converges or diverges. And we are going to use this truth. 1 over x to the p converges if p is a number bigger than 1, and it diverges if p is a number less than 1, right? Like a half, which would be what, 1 over square root. So suppose I wanted to do the integral, and I want to just do a comparison test of 10 over x cubed. Does that converge or not?
Converges.
Right. And what you do is you notice that p is equal to 3, which is bigger than 1, so it converges. Does it matter that that 10 is in the top? It still converges, right? Would it matter if there was a 3 as well in the bottom? No, still converges. So when you do these, what you do is you convert it, even if you don't physically write it, you convert it into what it's equivalent to. Doesn't this one behave the same way this one does, and that means converges? Does that logic make sense? Multiples of things that converge still converge. If the thing was infinite, do you think sticking a 2 in the top is going to help it any? Won't it still be infinite? It'll still diverge. So how can we use that on more complicated questions? I would like to know, does this converge or not? So what I have to do is I have to do some sneaky algebra. And I have a name for this process. I am going to call this process, you're going to do some surgery on it. In the big scheme of things, since you're only interested in what this integral looks like as x gets infinitely large, why can I say that this behaves like this?
Those are the highest powers.
Right, and would you agree when x is a trillion, won't a trillion squared be massively more important than just a trillion? And this simplifies down to that. And what do we know about that guy? Does he converge?
Yes.
And that is your answer. In fact, your homework answer is one of 2 words, converges or diverges. right? That's it. You only have 2 dots. So I guess if you don't know, you can guess eventually, but it's better if you know. And why is that helpful? If you've got a really ugly quadratic and you're going to have to get the answer right, and it's going to be a U sub and it's going to have messy stuff in it, wouldn't it be really nice to know if it diverges? Because couldn't you just say diverges and save yourself 20 minutes to find out it diverges? And if it converges, doesn't that mean that you then will know at the end whether or not it worked? Because if you do the whole thing and at the end you think it diverges, but you know it shouldn't, then you know you've screwed up. So it's a kind of shortcut pseudo checking process that allows you to check a little bit at least. But I don't pay any attention to what number it would eventually equal, right? So let's try another one with polynomials, and then we'll make things really weird. Okay, suppose I was doing that. If you didn't pick it up from the last one, what you do in this situation here is, do you notice that the highest power of x is the only ones that really matter, right? The leading powers, right? The biggest. So in the big scheme of things, when x is billion, billion, trillion, won't x squared overwhelm that guy? And what would 5x cubed get you? -1.
X cubed.
Well, yeah. Do we really need the 5? Not really, right? Doesn't this behave like a 1 over x? What do you know about 1 over x? Converge or diverge?
Diverge.
And we are done. Well, let's make it weirder. No, I refuse to. I can't. My brain refuses. Inverse tan of x. 2 plus e to the x, right? This guy is essentially question 25. Okay, squiggly lines. 2 plus e to the x behaves like e to the x. Inverse tan of x. That is not obvious what that thing is worth. So let me ask you a question that a lot of people have forgotten, or maybe never knew. Do you know the inverse tan of infinity is basically the limit of the tan function, right? As x goes to infinity. If you do the inverse tan function, can you trust me it looks like that? Do you know that it levels off at a number? What number is the inverse tan of infinity?
1.
I wish it was. That would be the nicest number. It's a good guess, because actually some questions it is, but not this time.
Is it pi over 4?
You are even nearer, but change the 4.
2.
Nailed it. Now, that isn't a 1 over x or 1 over x squared, but you should be able to look at that and tell me if it converges. And if the pi over 2 bugs you, then look at that. Does that converge? What's your gut feeling? I'm taking it before you change your mind. It does converge. But if you weren't sure, couldn't you simply just get the answer? Now that answer will be a number and it does converge, but that number is not what this is equal to, right? It just means it converges to something And the reason is that that is not the same thing as that. What that behaves like this is not the same number as this. And that is a big difference.
Professor,
Yes.
I'm confused on why it converges, because isn't it only when p is greater than 1?
Ah, but that is not a 1 over x squared story. This is a new story. This is a 1 over e to the x story.
Okay. Is there like a different rule for that kind of?
There's, well, I wouldn't call it a rule. I would just say I know what it is. And if I don't know what it is, then I calculate it. So the only one we have a story for are these guys here. Right? We have a rule for them. Everything else, you just take it and you simplify it down to the simplest looking thing you can get away with. And then whatever way this behaves, the original should behave the same. That's essentially the strategy. Now, in this particular case, it behaves like 1 over x, and I know that the integral of 1 over x converges. And that means that this guy also converges. So there is no rule for the others. Hopefully you can recognize them. If you've done enough questions, you will have you'll probably have met them. Right, time to start improper integrals. Might as well use this one. The integral from 0 to 4 of 1 over x minus 4 squared dx. And we do a limit thing. When we do a limit, it's t tends to thing. But when you've got a type 1 improper integral, it's not that the limits of integration have infinity, it's that the function has an infinite, and normally a vertical asymptote. Would you agree in this case it's at 4? So what you do is you put a 4 here, and that stays put as a 0 in this case. And then you do the limit as t tends to 4, technically 4 minus, because it's coming in from the left side. So now we're going to have to look at how do you do limits as t tends to a number rather than t tends to infinity. Okay. This fella here, whoops, my apologies, that's a t. This fella here can be rewritten as that guy. Are you comfortable with this fraction becoming this negative power? Now, why am I doing that? I'm doing it so I can integrate it. And isn't this basically the linear shortcut method? So I can use the power rule. So let's see what we get. It's going to be the limit as t tends to 4 minus of, add 1 to the power and divide by the new power and evaluate it at x equals 0 and finish at x equals t. Are we okay with this power rule integral? Right. Add 1 to the power, divide by the new power. Suppose that had said 3x minus 4, because it could. It'd be 3x minus 4 to the power of negative 1, right? That would still be there. But what would the 3 give me? How would I change this if this was 3x minus 4?
Third out of
You
it.
get a third, right? So you get negative a third. So that's how you cope with it. That's what I mean by the linear shortcut method. Now, as I've done this in other situations, I'm going to do it again. Style points are going to help you here to figure out what the answer looks like. So it's going to be the limit as t tends to 4 minus of negative 1 over t take away 4, subtract a negative means it's a plus, put in 0, you get a 0. So it's plus negative a quarter, so you end up with negative a quarter. Are you okay with plugging 0 in there and subtracting? Okay. We can do a version of, well, it's not so much brute force.
Sorry,
Yes.
would that be adding 1/4? Because it's -1 over -4.
Well, it's take away a negative 4.
Oh, okay. Yeah. Duh.
But it's worth, because you know what I'm like, it's worth asking me to check it. Right, let's do the equivalent of plugging in 4 here. Would you agree that that's technically what you're trying to evaluate? What does 1/0 look like?
Infinite?
So does it not make the answer infinity, so it diverges? So if you get a number, it converges, and it converges to whatever that number is. And if you get infinity out of it, then it diverges. We cool with that one? It's not exactly the same as t tends to infinity, but isn't a lot of the processes the same? Just at the end, you plug in a 4 instead of an infinity. If you need to, I guess you sometimes may have to do a L'Hopital. You know, if you get a 0/0 or something, you might have to deal with that. So there are, I can't find them now. Oh, 17. So this is like 17. So it's going to be the integral from 0 to 5 over 1 over the cube root of 5 take away x dx. When you look at this question, can you tell why it's a number 1, not a type 2? I mean, if it was a type 2, wouldn't that be infinite, or that would be negative infinite, right? And if these are numbers, then it has to be type 1, right? Yeah, it has to be something that's got a vertical asymptote. And it's pretty obvious that the vertical asymptote is at 5 and not 0, right? So now that I have all the features that I need, I'll do this, the integral from 0 to t. This fella is going to be called 5 minus x to the negative 1/3 power. Are we comfortable with what I just did there? That a cube root on the bottom is a negative 1/3 power. Have you noticed that you have to make these things powers so that we can integrate it using the power rule? And that is going to become I'm going to do the linear shortcut method because it's so much quicker. But you know, if you couldn't see that, or you're never really good at that and it's too much weird stuff, couldn't you just do a U sub on this and eventually get the same answer, right? So there is a backup plan. If you don't like it, do a U sub 5 minus x. But I'm going to do the linear shortcut method for integration. So it's a power rule, so you add 1. You divide by the new power. And then you pay attention to whatever's going on inside the brackets. 5 minus x. Right, well, basically, it's a minus 1x, isn't it? So what does that change here?
(1/5).
Negative.
Just negative 1. If it was, I don't know, 5 minus 2x, wouldn't you get negative a half here, right? If it was 5 minus 20x, you get negative 120 here, right? If it was 5 plus 10x, you'd get positive 1/10 there, right? So there's that little kink. Now, just like I do in every other situation like this, I convert it back into its original radical form. And now I can plug in the guys. If you plug in 2, you get -3/2, the cube root of 5 minus t squared. Take away a negative, so you're going to add 3/2, the cube root of nothing 5, 25. Now you plug 0 in there, you get 0, 5 squared gets you 25. It's a cube root of 25. Okay, almost finished. Now I can plug 5 in here. -3/2, the cube root of nothing squared, plus that guy. Would you agree that that's just 0? Agreed? And 0 plus that means that this converges, and it converges to that. Now, if I had left this question in that format, do you know that you're going to have to do things like 5 minus t to the 2/3 or 0 to the power of 2? You're just going to have some weird looking things that I think you're likely to screw up if you're not careful. Have you noticed that the strategy here is just kind of similar to making a limit, but it's a limit to 5 or a limit to 2, t to 5 or 2. But the math and the integration are the same. And at the end, don't you just plug in a number and you get something to do with 0, right? Rather than something to do with infinities. Right? So they do have a kind of sameness to them. This will have to be my last question. So this is 19. -2 is not a problem. X equals 3 is not a problem. Yet this is still an improper integral of type 1. Where is the problem?
There's a vertical asymptote at x equals 0.
So we split the question into 2 pieces because of that. I guess the equivalent is, do you know how, I think we only saw it once, but do you know how when you did the infinite ones, negative infinity to plus infinity, didn't you split into 2 integrals? Negative infinity to 0 and then 0 to plus infinity, that kind of split. Well, that's what you do if there is a vertical asymptote somewhere in the middle of -2 to 3 in this case. So you go and you get the answer to this one and you go and get the answer to this one. So will you all say hi before we forget? And give you a moment to think about that. Now, each one of these guys is going to turn into It finally got the thing to work itself out. It's going to turn into two separate questions. So here goes. Possibilities. Couldn't this one end up being infinity and this one ends up being 4? What would your conclusion be for this guy if that combination happened? What would you say about this integral if this piece was infinite and this piece was 4?
Diverges.
Diverges. Suppose both of them were infinite. Definitely diverges. Can you imagine this was infinite and this was negative infinity? Still diverges. Isn't there only one combination where this is going to converge? And isn't that combination where both of these are numbers? So if you're doing a question like this and you split it into two parts, which is this part and this part, if you do this part and you find out it diverges because the answer is infinity, do you need to do the second part? Do I need to find this integral if this piece is already, I've already done it and the answer was infinity and it diverged?
No.
No. So in a perverse sort of a way, aren't you hoping for divergers in these questions? And aren't you also hoping that if one of these is infinite, that you pick the infinite one first? Tell you my luck. Let's suppose that this was 2 and this was infinity, right? Just for argument's sake. With my luck, if this was 2, that's the one I'd end up picking first. And if this was 2, that would be the one. I always seem to pick the wrong one, meaning the one you have to do all the work for. Now, if both are numbers, then there's no big deal. Everybody had to do both, right? But can you imagine it would take me twice as long as somebody who got lucky?
Professor,
Yes.
could you, when you split it up, could you do the comparison tests on them?
The comparison test that we were talking about is only for the 1 to infinity kind of situations. It's only usable in type 2.
Okay.
There is a comparison test for these types of questions, but it's not worth learning because there's only 3 questions and it's probably easier doing it from scratch. But there is, if you want to go and look it up, there is a comparison test for type 1 integrals as well. But that's a perfect time, I think. Hopefully you've got enough here to work through our second section. So we'll see you on Thursday. And for Thursday and Friday, we're going to be looking at surface area and then your test on Monday. So I don't know about you, but I think the weeks are speeding up. They seem to be going faster now. That might be something to do with the amount of work we still have to cover. And I feel like, you know, I'm chasing a moving target, but I know we'll get it finished, so I'm not too worried. Okay, that's me. I'll hang around if anyone has any questions. Apart from that, have a nice day. See
Thank
you on
you.
Thursday.